In this video, we're going to look at a few more examples of the limit comparison test. Test the following series for convergence or divergence. Question A, summation k equals 1 to infinity, third root of k plus 1, divided by second root of k cubed plus 4. Question B, summation n equals 1 to infinity, 4n cubed plus 2n squared, divided by 2 to the n times n cubed plus 1. The hint is compare the given series to another simpler series, a p-series or a geometric series, whose convergence or divergence is already known. Let's look at question A first. We have summation k equals 1 to infinity, third root of k plus 1, divided by second root of k cubed plus 4. Now for large k, the dominant part of the numerator, so the dominant part of numerator is going to be third root of k, because adding 1 does not affect the magnitude of this ratio in a significant way. Similarly, adding 4 in the denominator does not affect this ratio in a significant way. So for large k, the dominant part of the denominator, is the second root of k cubed. So as k goes to infinity, the general term of our given series, which is third root of k plus 1, divided by second root of k cubed plus 4, is approximately equal to k to the 1/3 divided by k to the 3/2. If we simplify this and subtract off the exponents of k, we get 1 divided by k to the power of 7/6. So we should apply the limit comparison test with ak is equal to third root of k plus 1 divided by second root of k cubed plus 4. This is a general term of our given series, and our comparison series will have a general term bk is equal to 1 divided by k to the 7/6, which is incidentally the general term of a convergent p-series, because p is equal to 7 divided by 6 greater than 1. All right, so let's apply the limit comparison test. Let's form the ratio limit k approaches infinity, ak divided by b sub k. This is equal to limit k approaches infinity, third root of k plus 1, divided by second root of k cubed plus 4, divided by 1 divided by k to the 7/6. If we simplify this, we get limit k approaches infinity. We're dividing by 1 divided by k to the 7/6. That's the same as multiplying by k to the 7/6 divided by 1. That's going to be limit k approaches infinity, k to the 7/6 times third root of k plus 1 divided by second root of k cubed plus 4. This is equal to limit as k approaches infinity, k to the 7/6. Now, we're going to factor out k. So we get factor out k inside the radical. So we get k times 1 plus 1/k divided by, and we'll do the same thing to the denominator. We're going to factor out k cubed inside the radical. Second root of k cubed times 1 plus 4 divided by k cubed. That's going to give us limit k approaches infinity, k to the 7/6. And now you see why we factored out k. Now we can remove it outside the radical and write this as k to the 1/3 times third root of 1 plus 1/k divided by k to the power of 3/2, because we have second root of k cubed, k to the 3/2 times the second root of 1 plus 4 divided by k cubed. Now, k to the 7 over 6 times k to the 1/3, we have the same base, we add up the exponents, we're going to get limit k approaches infinity, and we get k to the power of 9 over 6 divided by k to the power of 3/2 times the third root of 1 plus 1 over k divided by second root of 1 plus 4 divided by k cubed. Now, when we take the limit as k goes to infinity, 1 over k clearly approaches 0. 4 divided by k cubed also approaches 0 because you have a constant dividing by something that's going to infinity. So let's simplify this. We get limit k approaches infinity. Now, 9 over 6 is the same fraction as 3 over 2. So these two actually cancel out. So what we have is third root of 1 divided by second root of 1, and that's equal to 1, which is greater than 0. So we have shown that the limit as k approaches infinity, ak divided by bk is equal to 1, is a constant, it exists, it's larger than 0. So therefore, since summation k equals 1 to infinity, our comparison series is a convergent p-series. 1 divided by k to the 7 over 6 is a convergent p-series. Why is it convergent? Because the value of p, the exponent of k, which is p is equal to 7 over 6, is greater than 1. Therefore, the given series that we have, which is summation k equals 1 to infinity, third root of k plus 1, divided by second root of k cubed plus 4, also converges by the limit comparison test. Also converges by the limit comparison test. All right, let's look at question B. Here we have summation n equals 1 to infinity, 4n cubed plus 2n squared divided by 2 to the n times n cubed plus 1. As n goes to infinity, the dominant part of the numerator, dominant part of numerator is going to be the highest power of the numerator, which is 4n cubed. That's the dominant term in the numerator. The dominant part of the denominator is going to be 2 to the n times n cubed. That's key. You have to multiply these to get the dominant term of the denominator. So as n goes to infinity, the given term of our series, which is 4n cubed plus 2n squared, this is a general term of our given series, divided by, let's multiply 2 to the n by n cubed plus 1. We get 2 to the n times n cubed plus 2 to the n. For large n, as n approaches infinity, this will be approximately equal to the dominant term, the dominant part of the numerator, which is 4n cubed, divided by the dominant part of the denominator, which is 2 to the n, times n cubed. N cubed cancels out. We get 4 divided by 2 to the n. This will be our comparison series. So we should apply the limit comparison test. Limit comparison test with a comparison series where the general term is bn is equal to 4 divided by 2 to the n. So now we can do the limit comparison test. So we have the general term of our given series, which is an is equal to 4n cubed plus 2n squared divided by 2 to the n times n cubed plus 2 to the power of n. And our comparison series, bn, is equal to 4 divided by 2 to the n. It can also be rewritten as 4 times 1/2 to the n. This way you can recognize it easily as the general term of a convergent geometric series. Why is it a convergent geometric series? Because the common ratio is 1/2, which is less than 1. So let's apply the limit comparison test. We have limit n approaches infinity, an divided by bn. This is equal to limit as n approaches infinity, 4n cubed plus 2n squared divided by 2 to the n times n cubed plus 2 to the n divided by 4 divided by 2 to the n. If we simplify this, we get limit as n approaches infinity. We're dividing by 4 over 2 to the n. That's the same as multiplying by 2 to the n divided by 4. So in the numerator, we get 2 to the n times 4n cubed plus 2n squared. In the denominator, we're going to get 4 times 2 to the n times n cubed plus 1. Notice we factored out this 2 to the n. Now, 2 to the n cancels out, and what we're going to get is, we're going to get limit as n approaches infinity, 4n cubed plus 2n squared divided by 4 times n cubed plus 1. This is equal to limit as n approaches infinity, 4n cubed plus 2n squared. In the denominator, let's multiply the 4 throughout, 4 times n cubed and 4 times 1. We get 4n cubed plus 4. How do we evaluate this limit? We divide by the highest power in the denominator. So let's divide by n cubed, divide by n cubed, and divide the numerator every term by n cubed. We're going to get limit as n approaches infinity of an divided by bn is equal to limit as n approaches infinity. 4n cubed divided by n cubed, we get 4 plus 2 over n in the numerator. In the denominator, we get 4 plus 4 divided by n cubed. Now, when n goes to infinity, 2 over n approaches 0 because we have a constant dividing by something that's growing to infinity. For the same reason, 4 over n cubed will approach 0 as n approaches infinity. This ratio is equal to 1, which is larger than 0, is a constant, exists, and therefore, since the limit as n approaches infinity of an divided by bn is equal to 1, this exists, is greater than 0. Let me write this better. Is equal to 1 greater than 0 exists. And we have summation. Our comparison series is a convergent geometric series. Our comparison series is 4 times 1/2 to the n, which is a convergent geometric series with common ratio, absolute value of r is equal to 1/2, less than 1. Then the given series, summation n equals 1 to infinity, 4n cubed, plus 2n squared, divided by 2 to the n, times n cubed plus 1, also converges by the limit comparison test. We always have to make that statement at the end of the question. Also converges by the limit comparison test. Limit comparison test. All right, thanks.